Hey guys, IBM is here with another episode of magnetic fields and electromagnetic induction. I think this is going to be part 13. This is part 13 of solved past paper questions in magnetic fields and electromagnetic induction. So question 33, a cathode ray oscilloscope is connected between the ends of the wire. The Y plate sensitivity is adjusted to 1.0 millivolts per centimeter. And the time base is 0.5 milliseconds per centimeter. That looks like an AS past paper question, but it is actually A-level. The Y is plugged at its center. The figure shows the trace seen on the CRO. Okay. Making reference to the laws of electromagnetic induction, that is Faraday's law and Lenz's law, suggests why an e.m.f is induced in the wire. Why an e.m.f is induced in the wire. The metal wire is held taut between the poles of a permanent magnet. A cathode ray oscilloscope is connected between the ends of the wire. The Y sensitivity is adjusted to those values and the time base to those values. The wire is plugged at its center. Okay, and the variation, the trace seen is this. So because the wire is plugged, the moving wire is going to cut the magnetic field of the magnet. And according to Faraday's law, there will be an induced e.m.f because of the cutting. The cutting causes a change in magnetic flux linkage. So I will simply say that the plugged moving wire cuts the magnetic field. Cuts the magnetic field, and by Faraday's law, an e.m.f is induced when there is a change or when there is cutting of flux. So the moving wire is going to intercept the field lines of the magnet, and therefore this causes a change in magnetic flux linkage, and by Faraday's law, an e.m.f is going to be induced. Then why the e.m.f is alternating. Now you notice that what is happening is an alternating e.m.f. It changes direction. It moves from one maximum to another maximum in the opposite directions. Now that takes us to Lenz's law. So by Lenz's law, the e.m.f is always the e.m.f opposes the change causing it. So as the direction of movement changes, it also means that the direction of the e.m.f must change. And hence the e.m.f is alternating as the direction of movement alternates. So by Lenz's law, the e.m.f opposes, or the e.m.f acts to oppose the change causing it, or the e.m.f opposes the change causing it. So as the direction of movement changes, changes, so does the e.m.f. Hence, the e.m.f is alternating as the direction of movement alternates. Hence, EMF is alternating as direction of movement alternates. So as the direction of movement changes, the EMF also changes direction, therefore it also alternates. Use figure 7.2 and the CRO settings to determine the equation representing the induced or alternating EMF. So I will start by finding the amplitude. Let me check peak to peak. Okay, so this is going to be the amplitude here. So we have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4.5, then and a half here. So those are 3 centimeters because each 5 small squares is 1 centimeter. So those are 3 centimeters. That is peak to peak, which therefore implies that the amplitude which is the amplitude x naught is going to be 3.0 divided by 2, which is 1.5 centimeters. That is the amplitude. Then length representing one cycle. For us to be able to find the period, we know that the period from the time-based setting, period is going to be the length representing one cycle times the time-based setting. The time-based setting is given, and so here the amplitude V naught was actually going to be 1.5 centimeters times the time voltage setting. Voltage setting was 1.0 millivolts per centimeter. So the voltage setting is actually, this is times 1.0 millivolts per centimeter, which is 1.5 volts. That is 1.5 volts. Sorry, millivolts, not volts. That is the maximum voltage. Then for the period, the length representing one cycle, I will say from, let me start from here, say between this point here and I think this point here. 1, 2, 3, 4, 5, 1 centimeter. 1, 2, 3, 4, 5, 2 centimeters. 1, 2, 3, 4, 5, 3. 1, 2, 3, 4, 5, 4. 1, 2, 3, 4, 5, 5. 1, 2, 3, 4, 5. Those are 6 centimeters. So period is going to be equal to length representing one cycle, which is 6 centimeters, times the time-based setting on the x-axis, which is 0.5 milliseconds per centimeter. So this is times 0.5 milliseconds per centimeter. So this gives you, this is 3 times 10 to the power of minus 3 seconds. Okay, so that is the period. We know that omega equals 2 pi over period. So omega is going to be equal to 2 pi divided by 3 times 10 to the power of minus 3, which is omega is 2 pi divided by 3 exponent minus 3. That is 2094 which is approximately 2090 radians per second. Okay, so the general equation is x equals to x naught sine omega t. Because this is an equation representing induced EMF, so it is V equals to V naught sine omega t. So the equation, if you want, you can use x, but I will use V. So the equation is going to be V equals to V naught, which is 1.5 millivolts, or you can write 1.5 times 10 to the power of minus 3 volts sine of 2090 times t, or you can write x equals to 1.5 sine 2090 times t, whatever you write, but this is the correct pattern. Okay, so that is I think that is fine, and that should be now easy. The poles of a horseshoe magnet measure 5 by 2.4 as shown in the figure here. The uniform magnetic flux density between the poles of the magnet is 89 milliteslas. Outside the region of the poles, the magnetic flux density is 0. So outside it is 0. A stiff copper wire is connected to a sensitive ammeter of resistance 0.12 ohms. A student moves the wire at a constant speed of 1.8 meters per second between the poles in a direction parallel to the faces of the poles. Calculate the magnetic flux between the poles of the magnet. So we know that magnetic flux equals to magnetic flux density times the area normal to the magnetic field. So this was 89 milliteslas, so that is 89 times 10 to the power of minus 3. And then the area, because this is 5 centimeters by 2.4, so 5 centimeters is going to be 0.05 meters times 2.4 is going to be 0.024. That is the area. So from our calculator, we have 89 exponent minus 3 times 0.05 times 0.024. So that is 1.07 times 10 to the power of minus 4. Because this is a flux, is in Weber, so that is 1.07 times 10 to the power of minus 4. Use your answer in A to determine for the wire moving between the poles of the magnet the EMF induced in the wire. EMF induced in the wire. Of course, EMF is directly proportional to or is equal to the rate of change of magnetic flux linkage. So EMF equals to the rate. I don't want to use E for EMF here. EMF equals to the rate of change of flux linkage. And of course, because the rate of change of flux linkage, this is going to be equal to change in flux. Because it's just one wire, I will not add the number of turns, so it is just change in flux over time. But then the time of cutting, is actually distance divided by the speed. Distance divided by the speed, and the distance through which it cuts from in the vertical plane is 2.4 centimeters in a time of 1.8 milliseconds meters per second. Sorry, the distance it is going to cut is 2.4 in the vertical plane at a speed of 1.8. So this is going to be 2.4, which is 0 0.024 meters divided by the speed, which is 1.8 seconds. So that is the time of cutting. Therefore, the EMF, of course, outside the poles, the EMF is 0. So the change in EMF is 1.07 times 10 to the power of minus 4 minus 0. So this is going to be 1.07 times 10 to the power of minus 4. You subtract 0 to get the change in the EMF. The time is going to be 0.024 divided by 1.8. This was meters per second. So when you simplify this, this is the same as just saying 1.8 times 1.07 times 10 to the power of minus 4 divided by 0.024. So 1.8 times 1.07 exponent minus 4 divided by 0.024. So that is 8.03 times 10 to the power of minus 3. Okay. Show that the reading on the ammeter is approximately 70 milliamperes. In other words, show that the current is approximately 70 milliamperes. So we know that current equals to V over R. And V is 8.03 times 10 to the power of minus 3 divided by R. What is the resistance of the ammeter? 0.12. So this is going to be equal to that answer divided by 0.12, 0.0669. 9 amperes. If you change it to milliamperes, that would be 66.9. Now, okay, this is 66.9 times 10 to the power of minus 3 amperes, which is approximately 70 milli. That would be approximately 70 milliamperes. If you round off to one significant figure, that is approximately 70 milliamperes. Okay. By reference to Lenz's law, a force acts on the wire to oppose the motion of the wire. The student who moved the wire between the poles of the magnet claims not to have felt this force. Of course, it must have been too small. Explain quantitatively a reason for this claim. When they say quantitatively, it means we must have a figure to back up our argument. So I'll find the force on the wire. This is going to be given as B, and the B was 89 milliteslas, so that is 89 times 10 to the power of minus 3. The current is 70 milliamperes now, so that is 70 times 10 to the power of minus 3. Then the length of the wire in the magnetic field is actually this section here, which is 5 centimeters. So that will be 5 times 10 to the power of minus 2, or 0.05. 0.05. So from my calculator, I have 89 exponent minus 3 times 70 exponent minus 3 times 0.05. So the force here is 3.1 times 10 to the power of minus 4 newtons. This force is too small to be felt. So the force on the wire of 3.1 times 10 to the power of minus 4 newtons is too small to be felt. So the student might be right. Electrons are moving through a vacuum in a narrow beam. The electrons have speed v. The electrons enter a region of uniform magnetic field of flux density B. Initially, the electrons are traveling at right angles. So they enter at this point at right angles to the magnetic field. And when a charged particle moves at right angles to the magnetic field, it experiences a force as predicted by Fleming's left-hand rule. The electrons follow a curved path in the magnetic field. A uniform electric field of field strength E is now applied in the same region as the magnetic field. The electrons pass undeviated through the region of the two fields. Gravitational effects may be neglected. Derive a relationship between V, E, and B. So, if the electrons pass through undeviated, it's because the magnetic force is equal to the electric force, and they are in opposite directions. Therefore, for no deflection or for no deviation, for no electron deviation, the force due to the magnetic field is equal and opposite to the force due to electric field. Therefore, the force due to the magnetic field is BQV. This should be equal to Q times E. Hence, because they said derive the relationship, I'll just make V the subject. Hence, V is equal to E over B. So the relationship is V equals to E over B. An alpha particle has speed v. It is an alpha particle whose mass, we know that the mass is 4u, the charge is positive 2e, and approaches the region of the two fields along the same path as the electron. Describe and explain the path of the alpha particle as it passes through the region of the two fields. Even though it has a different mass, a different charge, it has the same speed, and the speed equals to E over B. That is, the speed depends on the electric field strength, or equals to the electric field strength divided by the magnetic flux density. So if its electron is equal to E over B, it will still go through undeviated. So the question is, describe and explain the path of the alpha particle as it passes through the region of the two fields. And I've said, because the force due to the electric field and the force due to the magnetic field are both doubled, it means that E, B, and V have not changed. Note that the alpha particle and electron differ in mass, but mass plays no role in determining the path. Here, the charge of an alpha particle is twice the charge of an electron. So the new magnetic force, or I'll write Fm for magnetic force, would be B into twice Q times V. The new electric force, call it Fe, it will also be twice Q times E. So still it means V equals to E over B. So V equals to E over B, implying that still there will be no deflection. So the answer here is still no deviation or no deflection, because the charge and mass are not involved. Are not involved in the equation V equals to E over B. So if the mass, or you could say because the force due to the electric field and the force due to the magnetic field are both going to be doubled, so E, B, and V do not change. Both, or you could say the force, because both force due to magnetic field and due to electric field are doubled. Spelling of doubled is are doubled. So it means that E, V, and B do not change. When we change the charge, both the electric force and the magnetic force also change. They are both doubled because the charge is doubled. So it means there will be no effect on E, V, and B. Therefore, there will be no deviation still with an alpha particle. Okay. Positive ions are traveling through a vacuum in a narrow beam. The ions enter a region of uniform magnetic field or flux density B and are deflected in a semicircular arc as shown in the figure. Okay. The ions traveling with a speed 1.4 times 10 to the power 5 meters per second are detected at a fixed detector when the diameter of the arc in the magnetic field is 12.8 centimeters. By reference to the figure, state the direction of the magnetic field. Now that the arc is upwards, and yet the particles are entering perpendicular to the magnetic field initially, it means the magnetic force is towards the center of the circular arc, that is upwards. So if we use Fleming's left-hand rule, with the thumb pointing the direction of the force, the magnetic force, and the second finger pointing the direction of the positively charged particle, then the first finger must point into the page. It must point into the page. So by Fleming's left-hand rule, the magnetic force is perpendicular to the direction of the positively charged ions and the field. So with the second finger pointing in the direction of the positive ions just on entry, and the thumb in the direction of the force, that is towards the center of the circular path or upwards just on entry, then the first finger must point into the plane of the page, which therefore means that the field is into the plane of the paper. Into the plane of the paper or into the plane of the page. The ions have mass 20U and charge positive 1.6 exponent minus 19 coulombs. Show that the magnetic flux density is 0.45 teslas. Explain your working. So we have already said that the magnetic force provides centripetal force. Because the magnetic force provides centripetal force, so I'll just equate BQV to mv squared over r. Therefore, B is going to be equal to mv divided by rq. So we shall try to substitute. The mass is 20U, which is 20 times 1.66 times 10 to the power of minus 27. That is the mass. Then V is What is V? V is 1.4 times 10 to the power of 5. 1.4 times 10 to the power of 5, then divide by R. The diameter is 12.8, so the radius is 6.4. So the radius is 6.4 times 10 to the power of minus 2. Then times Q, which is 1.6 times 10 to the power of minus 19. So 20 times 1.66 exponent minus 27, then times 1.4 exponent 5 divided by 6.4 exponent minus 2 divided by 1.6 exponent minus 19. So that is 0.4539. Teslas, which is approximately 0.454 Teslas as required. Ions of mass 22U with the same charge, same speed as those in B are also present in the beam. On the figure, sketch the path of these ions in the magnetic field of flux density 0.454 Teslas. So of course we know that we have already seen that B equals to mv over rq, or we can say that R equals to mv divided by bq. So it means that the R is directly proportional to the mass. It means that R is directly proportional to the mass. So because this mass is greater, because V is the same, B is the same, they're entering the same field, and Q is the same, and R is directly proportional to M. Because this mass is greater, so a greater M means a greater radius. Therefore, we are going to draw a new path which has a greater radius than the one which we have here. So the new path is going to be this one here. I will have to erase this because it is no longer important. So the new path is going to be bigger than this one, but of course they entered from the same point. Okay, so this is going to be the new path. The detector should be around there if they are to be detected. Okay. And lastly, in order to detect these ions at the fixed detector, the magnetic flux density is changed. If we wanted to detect the ions at this point here, then B must be changed. B must be changed. Calculate this new magnetic flux density. So we notice that, or we mentioned that BQ is equal to mv of R. From the previous part, BQ is mv over R. Initially, we had B is 0.454 times the charge Q. The mass was 20 times U. The speed was V, and the radius was R. And now, this is initially. Now, we want a new value for B when the charge is the same, and the mass is now 22 times U. The speed is the same, and the radius should be the same because we want them to arrive at the same position of the detector. So this means that B divided by 0.454 should be equal to, I'm dividing, R cancels, V cancels. So this is going to be 22U divided by 20U, which means that the new value for B is going to be 22 divided by 20 times 0.454. So 22 divided by 20. 22 divided by 20 times 0.454, which is 0.499. So the answer here is going to be 0.499. Okay, so that should be the new magnetic flux density. If the radius is to be the same, the charge already is the same, but the mass is different. So if they are to be detected at the same diameter of 12.8 without moving the detector, then we should reduce, actually we should increase the magnetic flux density B to 0.499. Okay, so that is the end of part 12, part 13. Until next time, bye bye.